Good evening, Doctor. Good evening, Dr. Julius. I'm very happy to see you in the evening.
To continue with the day, we have Dr. Julius Gimbun to enlighten us on the topic of drug delivery by nanofiber scaffold prepared using a needleless electrospinning. Dr. Julius Gimbun is a professor and head of the Department of Chemical Engineering, University Malaysia, Pahang, Malaysia. He is also a Deputy Director of Center of Excellence for Advanced Research in Fluid Flow. He got his PhD from Loughborough University, UK. He has published several research and scientific article and book and he is also a reviewer of various reputed journals. His research interests are computational fluid dynamics, food and herbal processing, biofuels, reaction and catalysis, and particle technology. We are awaiting to listen your inspiring words, sir. Here comes Dr. Julius Gimbun. Over to you, sir.
Yeah, I think I'll get this shared. Can you see my slide from there?
No, Doctor. No, till now it's not visible.
It's not visible.
Yeah.
It's not visible. So, okay. Not visible. Is it visible now?
Yeah. Now it
Yes,
is.
sir.
Okay. So I think day is about 4 o'clock. So late afternoon, right?
Yeah, Doctor.
Good afternoon to
Yes.
all the conference attendee, and of course, thank you to the conference organizer, Dr. Peruso, for inviting me to deliver a talk in this conference. I believe you have a lot of good discussion by now because you start since in the morning, right?
Yeah.
Okay, so I think I just start with the presentation. I cannot see who else is in there, but I assume there are many colleagues, there are many professors are there. Good afternoon, and I hope you will enjoy this conference by Tan Bio. So today my title of talk is Drug Delivery by Nanofiber Scaffolds, prepared using a needleless electrospinning. This work was started, I think, about 6 years ago, and we do a little bit of work until now. We have a collaboration with Palms Connect. I believe Dr. Ranga is there in giving a talk at some time as well. We have Prof. Sridhar from University of Madras, Dr. Praveen, and basically most of the work is done by Dr. Ram Prasad. He'll be going back to India already. He completed his PhD study. So this is what we have. This one is needleless electrospinning that we have in the lab. So if you want to produce a large quantity of nanofiber consistently, I think you need some equipment like this. There are many types, but this is what the equipment that we have. So at first, we want to produce a good quality nanofiber, and then we want to study the drug loading, drug release, and we want to study some biological properties of the nanofiber. So nanofiber should have a large specific surface area, and they should have a small enough pore size for good breathability. And it should be possible to incorporate many different additives that bring many opportunities for drug loading or for other functional modification of the nanofiber. So for drug delivery, nanofiber is good because we have a large surface area for drug loading. And therefore we need only maybe a small amount of nanofiber to deliver the same medical effect. But this need to be studied further. So the first part of the work is the development of nanofiber scaffold. The conventional one using needles here, shown here in this one single needle produce a little bit of nanofiber in a collector. Normally can produce about 5 cm diameter of nanofiber in a few hours. But that is not sufficient for production of nanofiber scaffold that need to be produced in larger quantity. So what we have here is like a wire-based needleless electrospinning. We can electrospin many fiber from bottom to the top, anti-gravity, and in that way, because the larger surface area of this electrode, we can actually spin much more fiber. And then as shown here, instead of just one single fiber at the left, at the most right here, you can see that there are many sources of spinning fibers going to the collector. So in that way, we can produce a large enough amount of fiber in the shorter amount of time. So there are issues, there are things that need to be taken care of in the development of nanofiber scaffold. Sometimes viscosity too high, we get splash like this. On the most left, most right, maybe here. On the top here, we have a beading that is also undesirable. What we want is we have a good nanofiber with almost, I would say, uniform size or very narrow nanofiber diameter, like the one shown on the middle here. So there are many ways we can achieve that, but the easiest way is by manipulating the solution viscosity. We should manipulate it in a way that it is under certain viscosity regime. They call it intangible viscosity or something like that. It is not too dilute. Too dilute will get bead. Too viscous, there will be some splash or some sort of issues. So you need to adjust that viscosity just about right, but different polymer will require different viscosity for you to be able to get the right spinning. That is just one of the solution. There are other solutions as well, such as adding electrolyte, like salt can be added as well, so that we can spin better and we can remove this bead formation. So yeah, as I said, when you add electrolyte, you actually enhance conductivity, and the spinning is affected by conductivity anyway. So viscosity, conductivity, or humidity can be manipulated to get rid of this bead. But it's not limited to just those three effects. Just that these three parameters here is the one that is very easy to change probably, and easy to resolve whatever issues with the nanofiber making. So normally we will have something like this. I would not say that this is very good yet. This is probably just that we just about getting rid of the beads. We just about getting rid of the beads because what happened is we change those viscosity by adding more polymer, and then at one time when the beading is no longer there or very less, then we keep that particular parameters for the next run. It's quite easy to manipulate those viscosity. You just add more polymer concentration or can reduce the solvent amount in there. But then there are issues during the running of the electrospinning. The solution viscosity may get even higher towards the end because solvent can evaporate. It is not too much effect if you can do your electrospinning in a faster time. Like in the needleless electrospinning, we just run about an hour or so, then we can finish the whole thing, and the evaporation is minimal. So this is another issue. This is something to do with thick fiber. Thick fiber is actually produced by many different fibers entangled together. So they produce one big fiber. And sometimes it just splash because the humidity is not right for spinning. And probably sometimes the height of the collector is not quite right for the spinning. So we can adjust this height of the nanofiber collector, as well as we can manipulate the humidity. In our work, we rarely adjust the height of nanofiber collector, but we manipulate the humidity by adding the humidifier to the system, to the nanofiber, to the nanospider, needleless nanospider. So in the end, once you get your nanofiber, you would like to characterize them. Looking under SEM is one of the things that you can do. But then, of course, we need to know the fiber size distribution of it. So there are many ways you can do. If you have expensive software that can automatically detect each of the fiber, like here, this is done by Fibermetric software. The software will automatically detect the fiber and automatically get a histogram like this. That is one way of doing it. But if that is not possible, or you don't have those software, and there is a cheaper way of doing, we can do using ImageJ. ImageJ is available online. It is a free way. You just need the SEM image, and then you define the scale correctly, how many pixels or how many nanometer in X and Y directions, and then you start your measurement by picking the nanofiber one by one. It sounds trivial, but if you didn't have the automated software, then that is the way to do it. Some other people have a subroutine to do this as well in MATLAB. You can also download that from MathWorks, probably. What they do is the software will filter this image from black and white. They can then discriminate the fiber as well as the background, and then it can have algorithm to detect the fiber diameter and their frequency and so on. So all those methods is not exactly accurate. Sometimes, as you can see, sometimes the fiber, the intersection between the fiber is measured as well. So not exactly accurate, but it indicates to a certain extent the fiber size distribution. And what we want to see is how narrow is the fiber size. For example, like this, we have between 54 nanometer to 348 nanometer. Most of the fiber is within 150 nanometer. So that is a desired size for drug delivery applications. Okay, what happened? Here, another thing that we try is we try to embed a drug. We try to embed a protein. We try to embed titanosin. It's a chemotherapy drug. And then we try to measure, as well as we try to see the control release characteristic of the drug. So first here, after we embed the drug, we do a SEM-EDX. SEM-EDX will, they will have a greater penetration of the nanofiber, 200 nanometers. So if you have a nanofiber less than 200 nanometer, EDX will actually penetrate those nanofiber. So what you are detecting there is the amount of probably drug in the whole nanofiber. But when you run XPS, for example, you are detecting only at the top 2 to 10 nanometer layer. So you want to see whether the drug is on the surface or inside. So we can run this. It can give a qualitative analysis of where the drug is. So here, when we run the XPS, Xray photoelectron analysis, we can see that titanosin is barely detected on the surface. So what we can say is the drug is actually embedded inside. It is not actually a core sheet, but it is mostly embedded inside those nanofiber. It's not exactly like this one core sheet like this, but the drug is not on the surface because when we run this EDX, we can see is about 5% TI in there. So meaning it is embedded. The drug is embedded in the nanofiber. It is not on the surface. So there are many ways of embedding drug in nanofiber. You can put on the surface, or you can put in the middle, inside, as a core structure. This one is not exactly a drug. This is what you can see here is a salt added to a nanofiber polymer solution. If you add a salt, you can improve that nanofiber quality, but the problem is the salt will be deposited on the surface of the nanofiber. So again, it depends on the application. If salt is undesired in the application, then it is also another issue. But if the salt is not interfering with the application that you are intending, then it is probably acceptable to add salt to improve the nanofiber quality, and then to ensure that you have almost uniform nanofiber, but there will be a trace of salt on the surface. This is also another work that we have. We try to embed protein, because protein like BSA can get denatured. So what we found is even at 35 kilovolt of electrospinning, the protein is not actually denatured, meaning it will survive the process. And this indicates that if we have some kind of drug, protein type of drug, then it is suitable to use a nanofiber as well. So this is some of the analysis done for this sample with protein. So we can see that the protein structure is maintained, so meaning it is not actually damaged. And we also look into the control release kinetics of the drug loaded in the nanofiber. It is mainly a diffusion base, something like Cosmea-Pepas diffusion based mechanism. From the study that we have, we studied even longer than 48 hours, but here we only show here 48 hours. We have even for a few weeks of the result, because some of the application is maybe we need to use a nanofiber drug delivery as a patch, and that patch could be on the skin for more than 48 hours. So we also have those done, but for the purpose of the kinetic determination, we determine at 48 hours. We also did the MTTSA, and we found that it is biocompatible with 100% cell viability, meaning it is not toxic to mouse fibroblast cell line. And one of the applications that we are looking into is as a breast cancer drug delivery applications. This one is done by, I think this is the idea of Dr. Ranga, and he has been working on this for quite a long time. So here, we didn't have the clinical trial, but we do a cell line based study on MDA-MB231 human breast cancer cell line. With the nanofiber loaded with the drug for breast cancer, we can have 40% cell mortality for this particular human breast cancer cell line. So this particular study we are still doing. We have done a few tests already in the past year or so, but there are some inconsistencies, and we are looking forward to repeat again these studies with our collaborator in Madras and other institute.